All right, here we are, SAT 22 for week 12, and we have ourselves a non-multiple choice question, a student-produced response question. Let's take a look. So we have this equation, square root of quantity x minus 2 squared is all equal to the square root of 3x plus 34, probably a little bit more complicated algebraic equation than you're used to having to solve. What is the smallest solution to the given equation? And here's the spread of all the possible answers that we got here. And we have a clear spike here, clear winner, 80%, almost 81% said it was -3, which is the correct answer. No other really big spikes. There is one here at 10. 6 people said that it was 10, and makes sense because that's the other answer. It does have 2 solutions. How did we find our solution? Of course, mostly using Desmos, though a fair number of you phoned a friend. And we said, overall, this is a fairly medium question. I am going to bet, though, if you didn't get to use a calculator, it would have been skewed more heavily towards the harder side. But you know what? Desmos was our friend for sure, and it's probably the most sensible way of going about solving this thing. So the first thing that you would probably do, confronted by this, is just throw that thing straight into Desmos, just like you see it, and see what it is that it'll, see what this will do for us. Okay, let's see. So I want to, it was a square root, and then parentheses x minus 2, close those things, and square it. Watch what this is going to do. Boop, it has this V shape. I'll talk about that V shape here towards the end of the video, and make this thing equal to, and then we have another square root, and 3x, I think is plus 34, plus 34. Is that about right? Yeah. All right. Yep, sure is. Okay. And then whenever I zoom out, since this is not a function, it's only giving so we should only have a couple of dots on the x-axis, but the way Desmos graphs this is as vertical lines, and sometimes you're able to click on them and sometimes you cannot. This is one of those times where you can't click on them. And that's not too big of a problem because you could zoom in and see where it hits. This one looks like it's hitting at -3. And over here, this one looks like it's hitting at 10. But if it had hit at an irrational number for sure, it would be hard to gauge where those things are. So there is a suggested method of doing this, and that is to turn this thing into a function. So if I copy this equation down, I've got square root x minus 2 squared and equals square root of 3x plus 34. So essentially what I'm going to do is I'm going to subtract this over to the other side of the equation to make it equal to 0. 3x plus 34 is equal to 0. Now if I type this in to Desmos, it'll do the exact same thing as when we typed this equation in, and still the solutions won't be clickable to pull them into, let's say, the expression list, or even to see what their exact value is supposed to be. So there's one last thing that you do, and that is you pretend that this 0 over here is equal to y, and you're going to look for your solutions specifically on the x-axis. So these are x-intercepts for this graph. Right, and so this is, like I said, the preferred way of doing this, and this is pretty easy to do on Desmos. So just go back up here to this box, scroll all the way over to the left, and put a y equals. It's going to kind of freak out and not do anything yet because I got to change this equal sign here to a minus sign, and there we go. This is a kind of a strange looking graph. It still has like this little V shape to it, but it has a curve over here on the left-hand side, and it doesn't keep going like the other piece does. And the reason why it doesn't keep going is because there's going to be some negative values which make the square roots, the square root of 3x plus 34, undefined, at least for real numbers, and that's why it stops over there. Anyway, so now you'll find that it is pretty easy to just click on these x-intercepts, and you could pull them into the expression list, and you can see between the -3 and the 10, the -3 is the smaller of the two solutions. So there we go. Smallest solution, x is equal to -3. So again, this had two solutions, x equals to -3, or x is equal to 10, and the smaller of those two is negative 3. Okay, there we go. So that gives us our solution using Desmos. Now the question is could I have done this thing by hand? Well, obviously there were a handful of us, specifically, that is the wrong thing. There we go. What is that? 14.3% of us did this thing by hand, successfully or not. But here's how you do it. I'm gonna simplify the equation just a little bit, and let's just say, for example, I had the square root of x is equal to just 3. And I'm going to solve this equation for x. Now, this is something that you could probably do in your head going, hey, what could I take the square root of in order to get 3, right? You could solve it that way. However, what's happening is that we generally use inverse operations in order to solve an equation. This is telling me to take the square root of x, so I'll do the inverse of that by squaring both sides. So square and square. And what happens over here on the left-hand side is that we are squaring a square root, and as inverses, they should cancel each other out and give us just x back. That's not entirely true, and that's what I'll talk about at the end of the video. And then over here on the right-hand side, I would have 3 squared, which is 9. And of course, I can go, hey, the square root of 9 here is equal to 3. That seems to make sense. So that solves it for us. Okay, so I can do something similar over here. So let me kind of duplicate this, bring this thing down. So here's me solving this equation just straight up by hand. So I'm going to do the same thing I did before. I have square roots on both sides, so I'm just going to square both sides. And the square and the square root are going to cancel each other out, and it's going to leave the stuff that's on the inside here, which is x minus 2 squared is equal to, and then over here, a square and a square root are also going to cancel out, and it's going to be a 3x plus 34. Okay, and now I have myself a quadratic equation, and I know that I have a quadratic equation because I have this squared, and if I expand this thing out, I'm going to have an x squared term. So don't be tempted to like distribute the exponent here because there is no such property. Instead, what you have to do is x minus 2 times x minus 2, unless you know the squaring a binomial pattern, which some of you might from Algebra 1. If you don't, it'll be something you have to have memorized for Algebra 2. So when we go to FOIL this, our first term, x squared, outside, negative 2x, inside, another negative 2x, and then our last terms, positive 4. Just bring down the right side of the equation. Combine your like terms here. So we have x squared minus 4x plus 4 equals 3x plus 34. And so there is a way, based on a pattern, to go straight from this expression, this binomial squared, to go straight to what it expands out to here. Like I said, based on a pattern. Now, quadratic equation, remember, the method that we use to solve this thing is to make the right-hand side of this thing equal to 0. So I'm going to subtract out the 3x's and the 34. So x squared minus 7x, and then minus 30 is equal to 0. And, of course, just like we did on the previous one, you could put this into Desmos and make this thing equal to y and find the x-intercepts, but that kind of defeats the purpose of me trying to do this thing by hand. So now what I'm going to do is just try to factor this thing. I'm looking for two numbers that multiply up to negative 30, and that is this term over here. It would be that times whatever this leading coefficient is, but since I've got a 1 here, it's just negative 30. And then those same two factors have to add up to negative 7, which is the middle term there, of course, the b. So what times what gives me negative 30 and adds up to negative 7? I do believe that those numbers are a negative 10 and a 3, because negative 10 plus 3 is equal to negative 7. All right, now, with the AC method, what I do is I put an x at the ends of each one of those little factors, and I use it to expand out this little middle term here. So a negative 10x and a plus 3x, and bring down the rest. Now, there is a shorter way of doing this whenever the leading coefficient is 1, which I'll get to here in a minute. Let me group and group, and we can pull out an x from the first set, x minus 10 after I factor it out, and I can pull out a 3 from the other one, x minus 10, x minus 10 again, which is good because that's our new GCF. Factored out x minus 10 times x plus 3 for the other factor. Those are the numbers that are left out in front. And then using the zero product property, setting each one of these factors equal to 0. I got two things to multiply up to 0, so at least one of them has to be 0. So this first one, x minus 10 equals 0. So x is 10. And then for the other one, x plus 3 is equal to 0. So x is equal to negative 3. And then just like we saw before, the negative 3 is the smaller of those two solutions. So that's the one that I type in, right? Okay. Now, what I wanted to show you as an extension here is this left side of the equation. So you might remember whenever I typed in, I started typing this into Desmos, the square root of x minus 2, and then it was squared. Well, at first it treated this as a function, as in y is equal to that thing. And it turned out to be a V shape. Now, here's the thing that we think is supposed to happen is that the square root and the square are supposed to cancel each other out, thinking that this should be the equation y is equal to just x minus 2. But it turns out it's not. So let's see what actually is happening here. Diving a little bit deeper into this, so let me clear all this nonsense out. And I'm going to type in y is equal to just x minus 2, which of course is just the equation of a line. It's got a slope of 1, has a y-intercept of negative 2. However, if I type in y is equal to the square root parentheses x minus 2, close them and square them, you can see that you get this V shape, which is not exactly the same thing as just the line. And I can kind of turn this on and off, and you can see, what the difference is. And you can almost see as if the left side of this graph has just been reflected up above the x-axis. That's one way for us to think about this. So let me explain what's going on using sort of a simpler example. And that is, let's just look at a function f of x is equal to the square root of x squared, right? So I just kind of simplified it, got rid of that like negative 2 business, and that just shifts it over to the right anyway. So let's see by plugging in some numbers what this actually is doing. So let's say that I plug in a negative 1. So this is the square root of negative 1 squared. I'm squaring that negative 1 first, and I have the square root of positive 1, which is 1. And notice that what happened here is this negative and this number, they kind of, the negative sign just kind of canceled out. I didn't get negative 1 back, but watch what happens whenever I stick in a positive 1. So if I stick in a positive 1, square root of positive 1 squared is the same thing as the square root of 1, which is 1. Okay, here let's do the same exact thing with a different example. Say I do negative 9. So I'm going to plug in a negative 9 in here. And negative 9, I've got to square it first. So squaring it, I got the square root of 81. And the square root of 81 is positive 9. You can see that I essentially just lost the negative sign there. And then if I stick in just positive 9, square root of positive 9 squared is still square root of 81, which is equal to 9. So is there another function that does the exact same thing, that whenever I stick in a negative number, I get a positive number, and whenever I stick in a positive number, it essentially does nothing. It gives you the same number back. And the answer to that is sure. It's called the absolute value. And so often we say that squares and square roots are inverses of each other, and that is absolutely true if your number is positive. However, if your number is negative, though, it does make it positive again, and so they're not not true inverses on the entire real number line. Instead, they're only inverses when we take into consideration just the positive numbers. And in algebra, you'll talk about some domain restrictions when we do confront some inverse functions, like what is going on over here. And it complicates things just a little bit. Anyway, so that was a nice little deep dive into what this equation could give us as far as, solving it either on Desmos or solving this thing by hand.